welcome to this session of the lecture series on fluid inclusions in minerals. Over the past few weeks, we had a quick tour, or we browsed through the fluid inclusions that we encounter in different types of environments and different types of processes that are assisted by fluid. We browse through their characteristics, the methodology in brief as to how to look at them, and within the time frame of this lecture series, we discussed about the data that we could acquire from the microthermometric experiments of the diverse types of fluid inclusions that we see in the host minerals, which are also pretty diverse, while majority of them are actually done on quartz host. There are a lot more minerals on which fluid inclusions can be studied when the samples are taken from the relevant samples, the relevant rock exposures, when we study various environments and pertaining to various processes. And we have had a brief idea as to how to apply the results of microthermometric analysis to understanding of the processes in an ore forming environment, in metamorphism, and how the fluid inclusions are deformed, re-equilibrated, and how to overcome many of the problems that arise because of that, and how to make cautious and judicious interpretations to our data that we have acquired through microthermometry. Microthermometry gives us the very fast turn information about the fluid inclusion characteristics, and in turn the characteristics of the fluid that was responsible, or that gave rise to the rocks that we are studying with the problem that we have in mind to address. It is mandatory, there is no substitute to microthermometric analysis, and the instrumentation involved also is not that very expensive, and any fluid inclusion laboratory anywhere in the world can have such kind of fluid inclusion stage, or even more of such stages of different types. The one which we discussed could operate in a temperature range of 600 or 700 to minus 196 degrees Celsius. There are also other designs of this kind of microthermometric apparatus where inclusions can be studied at a much higher temperature. And for example, as we saw in some of the ore environment, the fluid temperature could be even higher than 600 degrees Celsius, and we will have a limitation of using stages which will operate between even within that particular range as 600 to minus 196. So, there are fluid inclusion stages which are designed to operate at higher temperature, so and also are suitable for study of the melt inclusions, which we have not covered in this particular lecture series. So now we would and we also have realized the limitations of microthermometric experiments, the results that is obtained from them in terms of the chemistry of the fluid inclusions. Although we have a good idea about the thermal regime, about the thermal characteristic, as far as the precise chemical composition of the fluid inclusions that we see would still involve a bit of oversimplification, like expressing them in weight percent NaCl equivalent, and even in case of inclusions which are rich in volatile species. So, in this particular week we will will attempt to discuss some of the methodologies and the instrumentation and techniques that are involved in analysis of these fluid inclusions. And any fluid inclusion microthermometric data and that is generated on any kind of samples that we are studying will be, if it is supplemented by such kind of analytical data, then the quality of the data or our understanding about the fluid is definitely enhanced, and we are in a position to present a little better quality of science than what is possible with only microthermometric data. Needless to mention that even most of the work that were being done in the earlier stages of development of this particular branch of study used to rely mostly on microthermometric apparatus, but still very primitive type of apparatus used to be designed, like the crushing stage, whose description will be available in some standard textbooks and old literature, where the fluid inclusions, if there is content in small fragment of the host mineral, can be crushed in particular in very specific type of liquid medium like oil or some medium of some specific gravity refractive index. The samples could be crushed and the volatiles released from those samples could be studied and at least have some idea as to what could the volatile could be. So, in this from this point onwards, we will be discussing about the analysis of fluid inclusions. So, if we look at, or if you see, we can either think of that we can analyze the sample in bulk and can have some idea about the characteristics of the fluid content in them, because from the various photographs of fluid inclusions that we have seen so far, we could see that they are variably populated with fluid inclusions of different types, and we can have some idea as to what could be the volume percent or mass percent of the fluid in any particular host that we are studying from while doing the routine petrography and examining the fluid inclusions in the minerals, and we have seen that there is a wide range of variations in them. So, keeping that in mind, we can possibly the analysis of fluid inclusions we can broadly categorize into two, that they could be either on individual inclusions or on the bulk. So, bulk analysis will always be destructive, because when we take a bulk sample and we extract the fluid inclusions from them by either overheating them in decrypitation or pulverizing them, crushing them in some liquid medium to get a leachate. So, it always has to be a destructive technique. So, this is bulk analysis, and we can also go for analyzing the individual inclusion, and those will be our microanalytical methodologies techniques using precise high end sophisticated equipment, and those kind of analysis also we could have either non-destructive or destructive. So, non-destructive in the sense that the inclusion will not be destroyed and can be further studied or can be preserved for any further type of analysis, or could be destructive, that we destroy the inclusion, take out the content from the inclusion cavity and do the analysis. And as far as the fluid inclusions are concerned, about the content of the fluid inclusions, we can think of in these three different broad components of them, that either we are basically would be attempting to estimate the concentrations of various electrolyte species, various aqueous species in the liquid, in the aqueous component, the liquid water component of it, the various cations and anions, or we could analyze the non-aqueous part. What we are saying is volatiles, also could be saying the analysis of the non-aqueous component like carbon dioxide, methane, nitrogen, H2S, argon and so on. What we have seen that fluid inclusions can have in appreciable concentrations depending on the kind of geological environment in which the process is operating, and the analysis of the solid mineral phases which are there in the cavity of the mineral, and in most of the cases they precipitate out of the inclusion fluid with changing pressure temperature condition when the particular mineral attains its saturation, or at times they could be accidentally captured solid phases. So, this will be the general idea about what we understand about the fluid inclusion analysis. So, the bulk destruct. So, when we will start with the, so before this, before getting into any of the details, it is to be kept in mind that this analysis of the fluid inclusion is the responsibility of the fluid inclusionist himself or herself, and unless it involves very high and very high sensitive high end equipment like a secondary ion mass spectrometer like a SIMS or a synchronous radiation X-ray fluorescence spectrometry, those which will always be operated by experts, and sometimes the analyst or the fluid inclusionist need not have to, or may not be possible on the part of the person to be getting a full details on the principles of the analysis of this with this kind of high end equipment, and at those situations we will only be interested in getting the result in terms of the what we actually wanted. But there are certain instrumental methods, certain analytical procedures methods which has to be carried out by the fluid inclusionist himself, because it is the background study which plays a major role in producing the quality of the data. The nature of the data and the quality of the data will be very much dependent on the care that has been taken. And some of these equipment which we can call as the small end equipment, like an ion chromatograph or a even sometimes Raman spectrometer, which we will be discussing in detail. Those instrumental details, the little bit of the working principles, it is always better to have some idea about them, and those we will be discussing to some greater degree of details. So, if we start with the bulk destructive analysis for dissolved species in the aqueous liquid, here we are limited by only releasing the aqueous liquid part and analyzing it for the dissolved anions and the cations. Some such procedure which is followed for a very good time, for a long time now, is the cross leach analysis. Essentially it means that we take take a particular weight of sample and we cross them in a deionized water, double distilled water, purified water, ultra pure water, which is free of any such dissolved species that we are interested to analyze, and then release the content of the fluid into that medium of the pure water, and then take the content and analyze in some suitable instrumental methods. Now, in some such kind of cross leach analysis, even though it is being practiced for a long time, but there are certain limitations. First of all, the thing that we have to keep in our mind, that the host mineral in which we want to study the or analyze the leachate, what we will get from this cross leach analysis is essentially a volume of the liquid, which we will call them as the leachate, which will be our analyte, in which we are interested to analyze the concentrations of different aqueous species. So, the purity of the host mineral, for example, if we want to analyze these ionic species like sodium, potassium, calcium, magnesium, iron, and the anion species like chloride, fluoride, and the bicarbonate and carbonate and so on, then it is always essential to see which host mineral in which we are going to do the study, carry out the study. They should have very limited solubility under the room temperature condition when we are crushing them in the deionized water. If they themselves will contaminate the solution, then the analysis will not be dependable, provided we work out to a great degree of details as to what will be the solubility of that particular host mineral, and then depending on the room temperature solubility, what concentration of any of the ions that it is going to contribute. But to the best possible practices, whenever we are doing it in a host mineral, we have to ensure purity of the host mineral. That means, if we are going to cross extract leachate from inclusions hosted in quartz, then we have to see to it that the samples that we are taking is pure. Study its textural relationship, if there are any other mineral that is associated with it, like phosphorus or some clay or some other phyllocetical mineral associated with them, or any other alteration mineral, and how to actually purify the sample, or how to get a pure fraction of the host mineral that we want. The another important crucial aspect is the inclusion types, their abundance, size and shape, because if we see the inclusions, there are so much of mixed type of aqueous and aqueous carbonic inclusions that we know that what exactly we expect here. Their abundance and size and shape will be a governing parameter, because there is a variation which we see in many across different samples that we take from different environment. Size and shape play an important role, because we are going to crush the sample in order to release the fluid contained in the inclusion. Then the quantity of the samples, actually how much we should cross, because here before we had precise analytical equipment available, these days in which very small quantity or very small volume of the analyte suffice for the analytical work. But before that, to get because if we say that in an ideal situation, if the a host mineral like quartz, if by doing some kind of a model analysis we know that okay, so this 0.1% in volume of the mineral is the fluid, and then if we want to extract a few cc's of this leachate, then how much of solid we must cross. So these days with the availability of high precision equipment like say for example an ion chromatograph, in which we can analyze with very small volume of the liquid as small as about 20 microliter or so, then we actually need very small volume of the leachate, and in that case we can also afford to cross a small weight of the sample, and because in order to extract a larger volume of the leachate, to cross the host mineral, since we still have to adopt to a gate motor type crushing of the pulverization of the samples, because we cannot do it in any other pulverizer, because in that case we won't be knowing exactly what kind of contamination we will be introducing. So it's always easy, that becomes the method becomes more adaptable if a small weight, say for example a fraction of 5 to 10 grams of the host quartz would be sufficient to release the fluid that will be calculating, and then the leachate that will be preparing just about within in a 10 to 15 cc of the purified water in which we will be doing the crushing, then will be enough for analyzing the leachate using some very high precision equipment like a ion chromatograph or a ICP-MS. So we should have some idea about the expected volume of the liberated fluid, which will be variable, and it will always be advisable if such kind of work could be done. For example, doing some model analysis in a computer assisted model analysis like in an image analyzing software in a program, if we could have such frames in which we can calculate the area percentage of the inclusions and then can integrate to have some idea about what is the volume percent of the fluid in the particular host we are studying, then we can have a better control, because we will be analyzing in our leachate, and then we have to back calculate in terms of how much of to the actually fluid, which was actually the volume of the fluid that likely to have been extracted, and you will have to multiply that factor to convert them to the composition of the inclusion fluid. And the major problem in this kind of an exercise is that when we are crushing a bulk of the sample, in the sample we know that there can possibly be more than one generations of fluid inclusions which are entrapped. So this needs a very careful study to actually ascertain as to how many, because we will not be possibly be able to circumvent the problem fully, but we can always see that what are the different generations of the secondary inclusions which are in the heel cracks, have some idea about them. In some of the cases it can always be that if we heat that particular sample to a certain temperature in which we know that the secondary inclusions, if they happen to be of a much lower temperature and much later entrapment in the host mineral, then it would possibly be it may be possible to get the secondary fluid liberated before we really go for the crushing of this particular samples. And we initially we are reducing the sample size to a few millimeters, so that we can keep it in a we can cross them in a agate mortar kind of procedure, and by that time also we would have possibly released a good amount of the secondary inclusions, but then they will still be there, and our results of analysis will always involve that degree of uncertainty which will arise from the presence of inclusions of many different generations. So, the sample preparation would involve a elaborate and thorough cleaning, and in this process of cleaning it will always be easy, it will always be advisable to go for cleaning or at a high temperature in using ultra pure water. And then maybe, because here if we will not be able to use kind of acids to clean the samples, because they will contaminate the analysis. For example, if we use nitric acid to clean our samples, then the nitrate concentration in our leachate may not be very dependable, and then it also, and so it would be advisable to go for rather kind of electrolytic cleaning to remove any other kind of adsorbed ions or any other elemental species that are there on the on the solid surface of the mineral. So, we need to do a elaborate cleaning before we can actually take the samples for extraction of the leachate. So, the crushing has to be done by again an agate mortar, and with within a purified water medium, and we reduce the size to what is attainable in a agate mortar, almost like a -200 Mess, which will be roughly about 75 microns size. So, that also gives us an idea that if we reduce the samples to a size of -200 Mess, what is the possibility, or what will be the percentage of the inclusions that are really likely to have been opened, and what volume of the inclusion fluid we would be expecting. And then we use the liquid medium in such a way that it make it up to a volume of known volume of the 10 or 15 cc. In most of the cases we use a 10 cc volume of the leachate and then now we decide that which method of analysis we are going to do, because ion chromatography will give the concentrations in form of the ions, and more precise analytical equipment like an ICP-MS will give the elemental concentration. So, it depends on the availability, but it is always advisable that we can do an ion chromatography analysis, and if possible combine the data with an IC, because ion chromatography will have a limitation in the ranges of the elements or the ionic species that could be analyzed. Although we know that in our sample, in our inclusion fluids, the major cations will be the sodium, potassium, calcium, magnesium, iron, and others will be in trace quantity. And sometimes we are also, if we are more interested in or you are studying essentially an ore forming environment, then it's we will be interested in estimating the base metals, the transition metals like iron, cobalt, nickel, copper, manganese, and in fact these are the areas in which lots of work or lots of research goes on, and these kind of instrumental analytical technique are constantly being upgraded, so that they become more and more versatile, and there is a provision for analysis of more and more of these ionic species. But ICP-MS would definitely have a far more range of the elemental species to be analyzed than in an ion chromatograph. So, I will just discuss a little bit about the principles of operation of ion chromatograph. So, ion chromatography essentially what we understand is an ion exchange chromatography. So, we can in a very simple way, and this within the limitation of this particular lecture series, we can explain that how it works. We have our analyte in a volume of 20 microliter minimum, or it can be sometimes we may need to little more, but a 20 microliter quantity could be enough, and that is injected to something which essentially we call as a column, which contains a phase which is a stationary phase, which is like some material which have come out through research. And the property of this particular stationary phase is that as and when the analyte is injected, the ions, all the ions in the solution, they will get attached or will be adsorbed or will be attached to this particular material which is there in the column, which is could be a resin or some kind of material which is has the property to do that, and the method works in the principle of release of those ionic species when they are attached to the mobile phase to be released at or to have variable retention time. So, that if we make a mobile phase which to elute the particular ions from the column, so they will be released at different they will have different retention time. So, they will be released very efficiently subsequently one after the other. It will be depending on their charge and their surface characteristics and many of the chemistry which cannot go into details very much. So, it is now this analysis, as we know, it is quantitative analysis. So, it will be working on standard based reference standard with known concentration. This kind of standard known concentration standard solutions can be prepared in the laboratory, which is routinely done for many of the cations, and there are multi anion standards which are available commercially or also can be prepared in the laboratory, provided one ensures very pure chemicals and also a very clean environment in the laboratory. So, it is essentially a quantitative method and needs to be well calibrated. So, it also works on the concentration ranges of the calibration standard, which we will be showing a little bit now. So, this analysis is sequential. The ions are analyzed one after the other. For example, in case of an anion, we will have fluoride, chloride, bromide, nitrate, phosphate, sulphate to be analyzed sequentially, and it operates on a restricted pH range of the analyte between 2 to 7. It is operated on a stipulated concentration range from 10 ppm to 10 ppb, but the beauty of this equipment or the efficiency of the equipment lies in the fact that we can prepare a linear calibration line in this range of several orders of magnitude variation in the range of concentration. And the analysis needs ultra pure water, almost like 18 mega ohm resistivity water, and ultra pure chemicals. And this entire procedure works because when we see here that this analyte is injected to the column and the column is being constantly flushed by the mobile phase. The mobile phase in different types of analysis like anions and cations are well specified depending on the chemical principles. For example, for a typical anion analysis, we will be preparing a very low concentration of bicarbonate and carbonate, which will elute the anionic species like fluoride, chloride, bromide, nitrate, phosphate and sulphate at different point of time, and they are detected by various types of detectors. They could be, in most of the cases they are detected by a conductivity detector, which will give the response in terms of the concentration of that particular ion and the conductivity, that is the conductivity difference that is resulted because of the release of this particular ion, and when the conductivity is actually working on the having the electrode where the anions and cations are getting deposited and the potential difference is created, and its work on the particular principle. One can also have a UV visible type of detector for which is specifically used for the base like transition metals, where they are more on their absorbance and the absorption characteristics of this kind of elements, or there could be electrochemical detectors. Similarly, there are various types of various designs of various materials which are used as columns in analysis of different groups of anions. For example, cyanide will be requiring a different type of a mobile phase, different type of a column, and so the limitation is that the analysis in any case will be incomplete because it is not possible to analyze all the as of now. So, the limitations are actually getting overcome gradually, and one would hope that this kind of instrumental methods will actually give very precise and very complete analysis, because as we know that in any particular ionic analysis, if we measure the anions and the cations, ideally the summation of the charges of the anions and the sum of the charges of the cations should balance and within the permissible limit. And if we just measure a few anions like fluoride, chloride, bromide, nitrate, phosphate and sulphate, and some cations like lithium, ammonium, sodium, potassium, magnesium, calcium, definitely there will be a good amount of charge imbalance, but these serve very important purpose of characterizing the fluid in terms of the not only the ionic species, but their ratios there, and so that we see the spatial variation in the ratios of the different elemental species and can draw important inferences on the fluid evolution. So, here is an example that I have taken from a sample taken from Alanskan copper deposit, where you could see the fluid inclusions, aqueous biphase inclusions, and we could see that there are primary in biphase inclusion and also there are trails of secondary inclusions, and so we know that what kind of so if we could somehow get rid of the inclusions from the secondary trails, then it will our inclusions analysis will be more reliable, but we have to interpret the results within that framework. It is showing just an example as to how in ion chromatographic analysis this is a calibration, and this calibration can be checked with its root mean square error and the reproducibility and the statistics. And here is a typical example of a chromatogram for the different using one particular column, in which these 6 anions could be analyzed. Here we do not get any phosphate because the fluid that we extract, the leachate that we extracted possibly did not have a measurable concentration of phosphate, because every equipment has the concentration range and below which we say that it is below the detection limit and we cannot analyze it. So, you could see that this is how the peaks they occur on a chromatogram, which is the x axis is the time in minutes starting from 0, and we could see that it almost takes about 27 and 28 minutes for a leachate to be analyzed for its anion concentration. On the y axis is the conductivity in terms of microsiemens per centimeter, and we could see that a very nice and a very straight baseline, and we see the peaks here. And when we have our reference standards in which the concentrations are known in ppm to ppb ranges, then from that by taking the area covered under the curve, which is also done for the standards, the concentrations, absolute concentration of these anionic species is calculated from this kind of chromatogram. And this is an example of a analysis of cations: lithium, sodium, ammonium, potassium, magnesium and calcium. So, these are the analysis which is done by, again similarly the same conductivity detector, where the conductivity is plotted on the y axis and the time is on the x axis, and you could see similar kind of duration of time is required for, and it is always advisable to have such kind of peaks well separated, so that the peak area could be accurately measured. Sometimes if the mobile phase element concentration is increased, then we can always get those peaks or get the total time of analysis reduced, but there should be a trade off between what could be the how much of time that is to be afforded for this analysis versus the dependability or the accuracy, and it is always advisable to have the prescribed concentration of the mobile phase, so that we could get very well workable the peaks of this kind of the ionic species for the dependable analysis. So, this is an example that of the analysis that we got from the cross leach fluid from a Alanskan deposit. This we could see that as expected amongst the cations, the sodium is the most dominant one, and amongst the anion is the chloride, which is most dominant one. Is going to almost like 23%, say 1%, 6%, 9%, 23%, which is shown on red, and the sodium also is the highest, with presence of potassium and calcium, which we could correlate from the observation of fluid inclusion freezing studies, and also the concentration of copper. So, these help us in making important interpretation in terms of the fluid chemistry and its variation in space. And as you could see here that the different ore types from the deposit, which is labeled as RQ for reef cores and VQ for the veins. We could also make a very good comparison between the fluid characteristics of from the different regimes and can draw important conclusions. And moreover, we could also make comparisons to some situations which we would like to compare. For example, thinking that it could represent a geothermal system, we could compare the fluid compositions with some known geothermal fields like the Broadland geothermal system in New Zealand, or Steamboat, or the Salton Sea. So what we could see that okay, the higher calcium content is for low Na/Ca content in all the samples, all the geothermal field, but Salton Sea is possibly a little more briny than what we see in the balance situation. And this is just an example as to how we can use the ion chromatographic data, and understandably there could be many more queries and curiosities, questions will be there, but it's always better to refer to some standard materials for better understanding of the analytical protocols and procedures for enthusiasts and people who want to utilize and exercise it or practice it on regular basis. So we will continue our discussion in the next class on the analysis of fluid inclusions. Thank you.